see evidence of black holes in terms of what they do to the light around them, something called the gravitational lens. So the red dot right in the middle of this slide is a bright galaxy with a massive black hole at its center, and behind it is a blue galaxy that's been massively distorted by the gravity of that black hole. We also see evidence for black holes in the center of our own Milky Way. This image is actually built from real data taken over a long span of years. You can watch the clock going in the upper left. And that yellow cross shows the position of something called Sagittarius A star, which is the supermassive black hole at the center of the Milky Way. We can watch stars moving around that seemingly empty point in space and watch what gravity is doing to them. You can watch this one star very nearly fall in. We keep waiting for it to fall in. It's going to be fun when it falls in. But that shows us that there's clearly something incredibly massive sitting there that is what we would describe as a black hole. But the question still remains, what does a black hole actually look like? So this is not the fault of the screen. You know, black holes, they don't look like anything. Ha-ha. We can't actually see a black hole because of this fundamental idea that the light from inside a black hole cannot escape. What we can do is observe the matter around a black hole. We know that that matter is going to be emitting light in what we call the submillimeter part of the electromagnetic spectrum. So this is the entire spectrum of light shown on the bottom of the screen, and it goes from very short wavelength light on the left to long wavelength light on the right. Our eyes can't see submillimeter light, but we've built telescopes that can. So we can't quite get a look straight into the heart of a black hole, but we can see material around it, and we can see this long wavelength light that it emits if we have the right kind of telescope. So it might not be exactly what we would imagine, but it's still pretty exciting. So a month ago, a press conference was announced declaring that we were going to be seeing the first ever picture of a black hole. And if you know any astronomers, everyone pretty much did this. We were pretty excited. There we go. Actual depiction. So, I had been learning about black holes since I was 5. I remember learning about the speed of light and running over to the light switch in my room and flicking the light switch on and off and watching the lights turn on almost at the exact moment that the light switch was touched and figuring, yeah, that's moving pretty fast. So I knew about black holes. I didn't know much about household electrical wiring, but it made sense. I've been excited about black holes for forever, so have most astronomers, and everyone was eagerly awaiting this image, and Hollywood had prepared us for what a black hole was going to look like. There's all these gorgeous depictions of how it might look as we travel toward it to escape death or find out about love. So we were all sitting and waiting eagerly. It was 6 in the morning here because they insist upon having press conferences on East Coast time. And the picture of a black hole, finally, after long times of waiting, emerged. So there were a number of internet think pieces commenting that this was maybe a touch disappointing. That after the lead-up, we were all celebrating a fuzzy, glowy donut, whereas all of the astronomers involved got one look at this picture and were immediately recreating the minion with excitement. We were still pretty excited. And the reason comes when you think about what we're photographing, how complex this is, and what exactly it took to get this picture. So first of all, we can talk about what we're actually looking at. This is a supermassive black hole sitting at the center of a galaxy called Messier 87. It's 53 million light years away. I mentioned before that a black hole that was about 6 billion solar masses would fit in our solar system. So the little white smudges that you can barely see at the center of this image show you what the orbit of Pluto would look like relative to this picture. To put this another way, I am currently holding up a quarter in my hands. How many people can even see the quarter? All right, I'm impressed with the people in the back. Can anybody read the date on the quarter? What about if I sent the quarter to New York City? Because that's the scale that this image is on. You would be able to read the date on a quarter in New York City from Seattle if you were taking an image of this high equality. So we think it looks fuzzy, but it's because we are fairly dramatically zoomed in. It's also not exactly orange. We've colored it orange to simulate what it would look like if our eyes could see in submillimeter light, but this is the submillimeter light that's being emitted from matter around that black hole. So the big black hole at the center of the image is not the black hole. It is the silhouette of a black hole. That black hole is distorting the light from the matter around it based on how incredibly powerful its gravity is. So it's actually lensing the light that would normally be coming straight at our eyes and is giving us a silhouette that's a few times the size of what that black hole would actually be. The light around it is showing us infalling material near the supermassive black hole that's emitting submillimeter light. You'll also notice that it's a little bit asymmetric. What that means is that this material is moving at nearly the speed of light. So as material moves toward us, it actually looks brighter. As it moves away from us, it actually looks dimmer. And they actually got good enough data on this that they could tell us that the black hole is rotating clockwise, which is a ridiculous amount of detail. So okay, how did we actually accomplish this? How did we read the date on a quarter in New York from Seattle effectively, observing a galaxy 53 million light years away? We used an incredibly huge telescope. And it's good to understand why, in astronomy, we're constantly pushing to using bigger and bigger telescopes. There's two perks to trying to make a telescope as large as possible. The first is that you get a bigger area, which gives you a brighter image. This is the same reason that your pupils will dilate in dim light. If you actually fill in that entire area, you've got a huge amount of glass that can collect and then bounce and focus photons so you can see very dim things that are very far away. The other appeal is the diameter. As the diameter of a mirror gets bigger, you get a sharper and sharper image. So this is kind of like using a telephoto lens to get a really clear picture of something very far away. In our case, what we really care about is the diameter. This black hole is emitting plenty of light. It's just emitting it in a very tiny area. So we want all the advantages of a telescope that in this case turned out to be the size of our entire planet. So I'm not saying that we didn't have options, but budget tends to be a thing, and we wanted to try and do this as reasonably as possible. We don't need the collecting area of this entire planet. So what we can do is effectively imagine a telescope with this diameter, but without all of that reflecting capability. You can imagine a mirror that only has a handful of reflective spots scattered across it. And this is what we wound up doing. This is the Event Horizon Telescope. It's a collection of 8 submillimeter telescopes spread across the entire planet. These are the 8 telescopes themselves. These are their names. I swear to God, these are their real names. Astronomers are the worst at naming things. Like a couple of them are named for where they are. The South Pole Telescope. It's not the, oh my God, awesome, incredibly cold telescope. Some of them are the millimeter telescope or the submillimeter and submillimeter. Yeah. But the big appeal of these is the fact that they were scattered across the globe and the fact that we could sync them up using something called very long baseline interferometry. So with this technique, you can take 2 telescopes and point them at the same thing. In this case, our little black hole. Our black hole will eventually emit light that is collected by those 2 telescopes, and together they can simulate a telescope that's the size of the baseline between them. As you add more telescopes, you get more collecting area, but you also get bigger baselines and more baselines to work with. So you can start to go kind of nuts with this and build up a large array of telescopes all over the planet that work really well. So what I just described in about a minute is a ridiculously complicated thing in astronomy. It is much more difficult to do than it is to say. So I want to point out a few of the challenges that come into play when we try to do very long baseline interferometry across the planet. First of all, these telescopes are all in very high, dry places. Submillimeter light is able to escape from matter near a black hole, but it boings right off water vapor molecules in our atmosphere. So we have to build these in places like the Atacama Desert in Chile. This is at an altitude of 6,000 feet and change. People who work up there will use supplemental oxygen while they're working at the site. We'll build these in places like the South Pole, which is actually at an altitude of 9,000 feet, and it will sometimes have an effective altitude of even higher because the Earth's atmosphere is so thin at that pole of our planet. The South Pole Telescope is also actually a desert. When you see photos of snow and people fighting through what look like blizzards, they're actually mostly walking through glowing snow. Precipitation at the South Pole is almost non-existent, which makes it an interesting place to work, but an amazing place for a telescope. We also need these telescopes to be customized to work together. All 8 of these telescopes were built as separate facilities. Team members from the Event Horizon Telescope traveled to the South Pole, to the Atacama Desert, to Mexico, to Hawaii, to Arizona, to retrofit every telescope such that their data could be effectively combined. Each one also has a few of its own weird quirks. So this is the James Clark Maxwell Telescope on the summit of Mauna Kea in Hawaii. And it looks a little strange. It doesn't quite look like the dishes that I've been showing you because there's this weird shroud thing over it. That is actually a vortex shroud that stays on the telescope at all times, even when it's observing, because sub-millimeter light can penetrate through it. But it does protect the telescope from wind, from blowing sand, and from what they very adorably, euphemistically refer to as birds. So this is what they mean. They don't want birds pooping on the telescope. We also have some telescopes in the array that are arrays in their own right. The Atacama Large Millimeter Array, or ALMA, has a suite of many dozens of dishes all working together already, so it's like this Russian nesting doll of arrays. All of those telescopes work together to get one data point that's then passed back and shared by these 7 other telescopes. In addition to having telescopes all over the world in hostile environments that weren't originally designed to work together, we also ran into the problem that the clicker didn't work, and we needed to know exactly where every telescope was in the array. So every telescope was sent a military-grade GPS for good reason. This sounds like a weird problem, but Hawaii and Chile are pretty well known for having earthquake problems, and the South Pole Telescope actually was moving. The ice sheet at the South Pole moves at a rate of 10 meters per year, and effects of this slow drift actually had to be removed before we could start working. We also needed good weather across half of the planet at the same time. So in April of 2017, these observations started, and they actually had to pause for a few days because there were thunderstorms at the Large Millimeter Telescope in Mexico. There were problems with the Sub-Millimeter Telescope in Arizona because of high winds. So collectively, we had to wait until conditions were perfect at these 8 very disparate locations before we could get data. And then finally, we had 5 petabytes of data when these observations were done. So for context, that's a 227-year-long video. So you can't email that. You can't upload that to the cloud. We actually had to store the data on special hard drives and ship it to computational teams working to combine it in Massachusetts and Germany. Again, this is easier said than done because the data were taken in April. That's winter time in the South Pole. And in the South Pole, planes don't start taking off until November. So that data was 6 months awaited by the team who was working with it at Haystack. They were describing the FedEx guy reacting when they showed him the package, saying it's like they thought we were expecting penguins to jump out of the box. He must have been really confused to just open it up and see hard drives. So, I've been talking a bit about movie versus reality astronomy, and I think we can agree that impressive as this image is, movie black holes might look a little snazzier compared to what nature winds up giving us. We can also definitely agree that the way that we do astronomy is significantly more interesting and exciting than what's depicted in the movies or in cartoons. What you'll usually see when you make an astronomer is some old white dude with a lab coat looking through a telescope with his eye, standing in a dome with the telescope like pointing out at it. There's papers scattered around. I don't know why he's wearing a lab coat. Our actual work is a great deal more exciting than this. I am actually writing a book about the way astronomers actually do our research. The book is called The Last Stargazers. It's due out in 2020, and every picture on here represents one of the stories that's going to be getting told in the book. You can also visit the book's website at the handy QR code. So I'll give you a preview of just a few of these before I wrap up. And the first one is the story represented up here by this log entry. So the log entry on the upper part of the screen is Doug Geisler's observing log from Monastash Ridge Observatory here in Washington on May 18th, 1980. Who knows what happened on May 18th, 1980? Mount St. Helens erupted, which was an interesting time to be working at an observatory. So for scale, this is a satellite image of Mount St. Helens erupting, and that's where Doug was. So Doug had an interesting day. His observing log starts off very normally. He had a nice clear night. It was the very... He woke up the next morning and opened the door to an absolutely black world. His flashlight showing maybe 5 feet in front of him. He thought it was supposed to be noon. He was terribly confused. And he was on an observatory summit by himself. He thought he was witnessing the results of nuclear war. Wandered back into the observatory, checked the radio, got just like salsa music at first, and then eventually picked up an emergency broadcast and wrote this amazing night log saying, "I am the last survivor of the war." Sky condition black and smelly. He was very thorough. So another one of my favorite classic observing stories is this one. So, this is the McDonald Observatory 107-inch telescope's mirror. Does anybody know what these might be? Bullet holes! Yes, somebody's heard this story. Bullet holes. So this telescope is in Texas. And as everyone will take great pains to remind you, the person who caused this problem was from Ohio. So they had a very displeased employee of the observatory show up at this telescope in the middle of the night and attempt to destroy it. It's a little unclear on what exactly kicked this off, but he started trying to hit the mirror with a hammer. When that didn't work, he took out a gun and fired 7 shots right into the mirror. Now this mirror is unbelievably thick, so bullets going into it did next to nothing. He was very disappointed. The authorities were called, he was taken away, but rumor of this spread around the entire field. The sheriff's office showed up and saw this big hole in the middle of the mirror and went, "Oh my God, the telescope's destroyed." They must have thought he had a bazooka. This is actually a very normal feature of any telescope mirror. It's a hole cut in the center of the primary so that light can be bounced off a secondary and then back into the instruments. But word spread around the field that something horrifying had happened, and the director wound up putting out a memo explaining to people what had happened and reassuring everybody that it was okay. The harm from the bullets, can someone change the slide? The harm from the bullets was extraordinarily small. What they actually wound up doing was digging out the bullets, painting over the bullet holes, and declaring that it was no longer a 107-inch telescope, it was 106-inch. So then the last story that I wanted to cover shows this image on the lower right. So this is a view of the Large Magellanic Cloud on a day in February in 1987. You can only see this galaxy from the southern hemisphere. It's a little satellite galaxy of our Milky Way. And an astronomer working at an observatory in Chile, a telescope operator named Oscar Duhalde, wandered out that evening and noticed that something was a little different. On every previous night, the galaxy had looked like this, but that star had appeared on the night he was observing. If you go to the next slide, you can see exactly how tiny that is in the night sky. This is actually a picture I showed you earlier of the Atacama Large Millimeter Array. So going back to what he was looking at, you can see that this would have been pretty hard to spot. Oscar knew the sky and knew this galaxy cold and recognized that some weird new star had appeared. He was working as an operator, he went back in and honestly didn't say anything at first. They were busy taking their observations. Eventually somebody else drifted over and said, "There's a new thing in the Large Magellanic Cloud. Do you think this might be a supernova?" And he immediately went, "Oh, yeah, I saw that earlier. I know exactly where it is. I know exactly where to point you to it." And this was actually the discovery of supernova 1987A. It's the closest supernova that's happened to Earth since galactic supernovae, which last went off in the 1600s. And Oscar de Halde is thus the only human being on the planet who can claim to have discovered a supernova with his naked eye. So, that is just a sampling of some of the incredible things that have happened to people while studying the universe. We point lasers and bounce them off the moon. We fly telescopes in planes. Occasionally telescopes collapse. We will sometimes fly telescopes via the moon. But all of these are what we do to try and get incredible pictures like this one. So on that note, I'll leave all of this up, and I'm happy to take any questions that you have. Thanks. And if you want more of these stories, go to the QR code. You can sign up to get updates on the book and free stories before it comes out. Okay, so this was a good question. It was about the telescopes around the world and who was funding it. Oh no. Anyway, the telescopes all around the world were funded in large part by the National Science Foundation, but it was actually part of a large-scale collaboration with multiple observatories around the world. This announcement of the black hole picture had simultaneous broadcasts in the US and Washington, D.C., supported by the NSF, and then at other sites around the globe so that everybody was seeing it simultaneously. For our part of the funding was the National Science Foundation. Other questions? Yes? So this was a great question. It was who was the woman standing behind all of the hard drives? I'd shown that picture of all the hard drives that had to get shipped all over the world so that we could computationally combine data from 8 different telescopes. The woman standing behind them was one of the members of the team at MIT that developed an algorithm to actually combine all of that data, which is an unbelievably difficult endeavor. It was an enormous team working on this. She was a young and brilliant graduate student on the team at the time who made some really wonderful contributions, and she got made the face of part of that aspect of the work. So her name is Dr. Katie Bowman, and she's just about to start a faculty job at Caltech. Okay, we've been thrown a challenge for what our next image is, because I've just been asked what this would look like in 3D. And whether what we're looking at is a disk, or if we were to pull this out of the screen and turn it on its side, whether we'd see something different. You can kind of imagine this is similar to a disk. When material is getting dragged into a black hole, it forms a disk-like structure, and we're lucky with the black hole in M87 that that disk is pointed almost face on at us. There's other black holes where we wouldn't be able to do this because we don't get that turn. What is Hawking radiation in relation to a black hole? Every time I give a black hole talk, I get a question that is just excellent and squeaks to the outer edges of what I know about black holes. As far as I understand, and I welcome other astronomers to help me out with this, Hawking radiation is an explanation for how a black hole could, in theory, radiate, despite the idea that nothing could actually escape. The mental picture I've always had of this in my mind is that you spontaneously have 2 particles form in space, a particle and an antiparticle, which should in theory happen all the time. Particle and an antiparticle form, run away from each other, come back, annihilate one another, and they're gone, and the conservation of energy is satisfied. Under the Hawking radiation model, this happens right at the event horizon of a black hole. So a particle and an antiparticle form, the antiparticle goes tumbling past the event horizon, and the particle just goes, sweet, I'm free, and is able to run away. So this is how we're able to see what looks like emission from a black hole. It resembles radiation, because what we're seeing is something radiating from a black hole. It's not, however, what we're observing here. Any Hawking radiation would be happening well within this dark area where the gravitational shadow of the black hole is walking in. Any other questions? Yeah. That's a good question. So what about special versus general relativity? So these are two different treatments of relativity. When you hear about Einstein, you usually hear about general relativity. And they're basically two different treatments of the same general question of what weird things happen to space when we start moving at the speed of light or when we start invoking tremendous amounts of mass. Everything that we're seeing here is a consequence of general relativity, from how the black hole looks to, as you pointed out, how those GPS units worked on the telescopes. We are able to use GPS and get very accurate GPS because of how well we understand general relativity. It was yet another test of Einstein's model of general relativity, and it fortunately worked extremely well. Any other questions? Good question. How did it do interferometry when the telescopes are too far apart to interfere? I showed you that picture of the Atacama Large Millimeter Array, where the telescopes are fairly close. They'll actually be connected underground, and the data will be combined right there on the spot. It's really just a matter of timing. If we know exactly where a telescope is and exactly when the data is taken, the data don't need to be combined instantly. In fact, the observations from Omaha are combined instantly. They theoretically go into the telescope and are then combined to the correlator building a second or two later. So it's, a second versus 6 months of flying the data from the same hole. The principle still works as long as we keep track of when and where the telescopes are very, very carefully. Really accurate. All right, one last question, and then we'll move on. And if there aren't any more questions, then thank you again, and stick around for our next talk.
our scheduled commercial break. Congratulations again to all our winners from before. I hope you came up and secured your prize. We're about to get started with our second speaker, and I've been thinking a lot for the last couple weeks about how to best introduce him. And so I'm going to introduce him in a lot of ways, even though you already know who he is. You may know him as a UW graduate student, both in astronomy and the astrobiology department. You may know him as the guitarist of the popular all-astronomer Seattle band, Night Lunch, of which I am wearing a shirt. You may know him as the recently minted PhD. And finally, you may know him as the last still local Seattle co-founders of Astronomy on Top Seattle. Please bring down the roof for Dr. Brett Norris.
Thank you. Thank you, everybody. So this is our 50th Astronomy on Tap in Seattle. Can we get it going for that? Out of curiosity, were any of you here the last time I spoke? I see a few hands. I talked about a black hole, and I talked about how we were going to use this network of telescopes that was going to see a black hole for the first time, and I was super excited, and I was waving my hands, and I was showing you all these pictures of what a black hole might look like. And then it happened less than a month later. I was so happy when that happened. For those few of you that were here, you knew. You knew before everyone else knew. Way to go. Good on you. So keep coming to Astronomy on Tap Seattle, because you'll find out about the astronomer's secrets before the rest of the world does. Today I'm going to talk to you about smaller stuff. And I think they're just as important. I hope I can convince you of the same thing. Over the last 6 years, I arrived in Seattle in 2013, and I got here thinking exoplanets are the single coolest thing in the universe. The universe is a big place, and there are a lot of exciting things, and black holes are super cool, and I'll get to talk about them any day, but planets could be the coolest because the planets are the things where you could find life. And as Nicole mentioned in her gratuitous introduction of my life, I just got a PhD in astronomy and astrobiology. And astrobiology is the study of where life could exist in the universe and how we can go look for those conditions in the universe. And maybe some of the best places to look are on planets, which are small and are dark and are less exciting than black holes sometimes. But what if they were exciting? I'm going to try to tell you that some are exciting. We'll get to that. But first, there's something that got in my way. When you study a planet, what you're really studying most of the time is its star. A planet is orbiting a star, and usually you detect the planet by some effect that it has on its host star. And so I spent the last 6 years in a giant tangent kind of studying stars by accident, even though I came here thinking I was going to study planets. And so I'm going to tell you a little bit about stars. I'm going to get to the planets because it wouldn't be a planet, I wouldn't be able to motivate this talk for you if it weren't for the planets that orbit those stars. And lastly, I'm going to tell you a little bit about the future. Instead of spending my time talking about what I've studied for the last 6 years, I'm going to look forward to the next 6 years and tell you about what's coming. And hopefully some of you recognize what that shape is, but that will make sense in a moment. So to begin, if you look at the sun at exactly the right time, and this person was looking at exactly the right time, on occasion something passes between you and the sun. The something in this image is up over here. That's the space shuttle about to dock with the space station, which happened to pass between an observer and the sun. And the observer had a very nifty camera that was ready to take the photo at exactly the right moment. This event in astronomy parlance is called a transit, when something passes in front of a star. And transits are really nifty. Here's a view of a transit of the sun by the planet Venus, which happened in 2012. If you missed it, I'm sorry, you're not going to see another one. It can take a long time to come back around. But Venus, on this one occasion, passed between the Earth and the Sun, and we happen to have a bunch of spacecraft that are staring at the Sun all of the time. And they took some really fantastic images of Venus as it passed in front of the Sun. What we're doing is we're watching the same movie again and again at different wavelengths of light. And you can see the Sun looks different depending on what wavelength you look at. You can see that the Sun is a very dynamic place. It's got a surface that's covered in features. It's got bright spots and dark spots. It's got variability in time. And all of that makes it complicated to study the planets that orbit stars like the Sun. But the way that we actually study this is not with this privileged view that we have of the Sun. When we're looking at planets in other solar systems, we have a lousier view. We can really only see the change in brightness of the star as a function of time. We can't zoom in far enough to see the planet the way we see it here. And the most successful mission at doing this, the mission that has discovered the most planets to date, is NASA's Kepler mission. Kepler is very special to me. For my departing PhD talk, I have to talk a little bit about Kepler because Kepler started observing the year I graduated high school, and it finished observing around the time I finished my PhD, and so I've kind of grown up with Kepler. And that's been a really special time to be studying planets and stars because Kepler has opened up a window into that universe that we didn't have before. It's discovered 2,300 planets, which are bona fide real planets. We know that they're actual planets. It's discovered another similar number, 2,400 planetary candidates, which are likely planets, but we need to do some more follow-up to figure out if they're real planets. And the way that it did that was using the transit method. When a planet passes between the star and the Earth, it blocks out a little bit of light. Only a little bit. And the amount of light that goes missing is proportionate to how big the planet is. If the planet's really large, it blocks out a lot of light. If it's really small, it blocks out only a tiny fraction. And it goes around in its orbit again and again and comes back and gives us one of these dips that you can detect from the Earth if you have a very careful photometer or photon counter, which we have. We have a really precise one on the Kepler spacecraft. And what it's discovered is bewildering. Let's just jump into the strange worlds that have been discovered. There are a lot of plots that people like to show you that describe what Kepler found, and usually they're just a mess of points, and there are two axes that don't seem relatable, and it's not really exciting. The exciting stuff is when they show you pictures like this, which of course we all know is fake, right? This is an artist's conception of what a planet looks like orbiting another star. We don't actually have a view like this. But I think one way that you can break down what Kepler found, because Kepler, as exciting as its results were, they were statistical. And I think there are some nerds in this audience who would applaud the statistical nature of the Kepler mission. Am I wrong? Yes. Okay. But there are some people who think statistics aren't as exciting, and for that I'm going to try to show you an image that sums up the statistics that Kepler has given us. For every Jupiter-sized planet that we've discovered, how many Jupiter-sized planets are there in the solar system? One or two. For every Jupiter-sized planet we found in the solar systems that we've discovered, there are about 2 Neptune-sized planets. And for each Jupiter-sized planet, there are roughly 12 Earth-sized planets. That does not parallel the solar system anymore, right? We have Uranus and Neptune, which are both roughly Neptune-sized, but we have 3 rocky planets in our solar system that are roughly Earth-sized. We don't have 12. That means there's a lot of those. And then even weirder, there's this other class of planets, which I don't have a picture of, and so I'm going to represent them with circles, which are between the size of the Earth and Neptune. There are 15 of those. So the most common type of planet that we've discovered is something that we have no analog for in the solar system. It means there's a lot of work that we have left to do. Here's a small picture of why we have work left. The biggest rocky planet in the solar system is the Earth. The next biggest rocky planet is Venus. Venus is almost exactly the same size as the Earth. The next biggest planet is the smallest gas planet. That would be Neptune. Neptune is 4 times the size of the Earth. In the solar system, there's nothing that falls in between these two sizes. But it turns out that that is what nature is best at making. Something that's between the rocky planets and the gas planets is what the universe makes the most of. We don't know yet where the cutoff is in radius or in mass, where planets are more likely to be rocky or to be gaseous. We think that that's near 1.7 Earth radii, but we don't know for sure. And one of the things that I think we're going to have better answers for in the next 6 years, when the new PhD students are graduating in 6 years, no pressure. There are a couple in the front row who just gave me a look. When they're graduating, we might actually have some answers as to where the boundary is between the rocky and the gaseous planets, but we really don't know the answer yet. We think that most planets that are smaller than 1.7 times the size of the Earth are rocky. And that's really interesting when you apply it to particular systems. And one system that I think is super cool that I'm going to talk about for a minute is the TRAPPIST-1 system, which was in your trivia questions. The TRAPPIST-1 system is super cool and deserves its own slot in this talk because it is host to not 1 and not 2, but 7 Earth-sized transiting exoplanets. That's a lot of planets. We don't have that many rocky planets in our solar system. Think about that for a minute. There's so many rocky planets in this solar system, it's like 2 of our solar system worth of rocky planets. They're distributed at different radii away from the star, so that some of them are too hot to support liquid surface water, and the outermost one might be too cold to support liquid surface water, but the middle 3 might be sort of near the right place, almost have liquid surface water, depending on the history of how the star's brightness evolved as a function of time, which is something we don't fully understand yet. But ignoring that caveat, there are planets that might be where liquid water would be in this solar system, which is super cool. Part of the reason why this system is so exciting is because of how small its red dwarf host star is. The star is shown here to scale next to the planets, and it's kind of hard to tell that it's a small star compared to the planets. But this star is the size of the planet Jupiter. It's more massive than Jupiter, but its radius is about the same size as the planet Jupiter. Why is that important? Well, here's a picture of the sun. We have a transiting bug. We have a picture of the sun, and we have a small TRAPPIST-1 to scale. We don't actually know what the surface of TRAPPIST-1 looks like. It might have bright spots, it might have dark spots, it definitely has flares. It does all kinds of things, but we don't have a close-up picture of a star like this yet, so we don't know what they look like. So I'm just using a red disk. If I were to put an Earth-sized planet in front of both of these stars, it would look like this. I'm sorry in the back if you can't see the Earth. The Earth is really small compared to a sun-like star. And the same size planet is proportionately larger, blocks a larger fraction of the surface area of a smaller star. So the motivation for studying these planets that orbit really tiny stars is that they block out larger fractions of light, which gives us a bigger signal to detect. Despite the difficulties, there are a handful of planets that have been discovered which seem eerily Earth-like. One that was really touted in the media as being like Earth 2.0 is called Kepler 186f. There are so many Kepler planets, we just give them numbers, we don't give them names. And Kepler 186f is in the habitable zone of its star, meaning it's at the right distance to have liquid surface water. It's 1.1 times the size of the Earth's radius, which makes it small enough that it's probably rocky. The star is a little bit smaller than the sun, but the planet's a little bit closer than the Earth is to the sun. So everything kind of works out to make us believe that this planet might actually be Earth-like. But again, you and I know that this is an artist's conception. This is not what we know about the planet. All we know about the planet is that it blocks out starlight. It's just a disk. That's all we get to see. And so we're going to have to do a lot of homework over the next 6 years to figure out whether or not that's actually like the Earth, right? That's what we're going to try to do in the next 6 years. And how are we going to do that? Well, we're going to use a new telescope. I don't know about you, but I see this and this gets me excited. Does that get you excited? Look at that telescope. Look at that gold-coated telescope. This is the James Webb Space Telescope, and you can see for scale some humans over here in little suits in a clean room. The James Webb Space Telescope is going to open up a new window in the same way that the Hubble Space Telescope changed the way that we see the universe. The James Webb Space Telescope is going to do the same thing. The reason I'm most excited about it is because it will be the first telescope that should be able to look at an exoplanet's atmosphere and figure out whether or not it has the right components for life to exist on that planet. Here's how that works. First off, we're all familiar with Hubble. We all love Hubble. Nobody's going to bash Hubble here. Nobody's going to shoot Hubble here. But Hubble was actually not that big a telescope. Hubble and the space shuttle were designed together. Did you know this? The space shuttle was designed to fit Hubble in it. Hubble was the biggest thing meant to go to space at the time. We've since built bigger rockets, and we've since figured out how to build more complicated mirrors which fold up. And so the James Webb Space Telescope is this big compared to Hubble. Yeah, I heard some oohs. I like that. That's how I feel too. Because the bigger your telescope, as Emily mentioned earlier, the more light you get to collect. And as astronomers, pretty much the only thing that we have to study is photons. Unless you work in the solar system and on occasion you get a sample of something. For the most part, we spend our entire day worrying about light. And the more light you can collect, which is represented by the larger surface area of this telescope, the more science you can get out of that telescope. And so what is the science that I want to do with this telescope? Well, they probably won't let me, but I want to do this with it. If we split up light that enters the telescope with a prism, and usually when people tell you a prism, it's a lie, but the instrument that I use actually has a prism. The prism on the James Webb Space Telescope is going to split up light into a spectrum. And the spectrum of light is going to tell us something really interesting. In the moment when a planet is blocking a star, there's a thin sliver of light that passes from the surface of the star through the atmosphere of the planet and then on outward into space to you. This is an image of the Earth taken from the International Space Station as the sun was rising from behind the Earth. And so you can see the atmosphere of the Earth lighting up. But I want you to imagine now that you're so far away, what you see is the sun taking up the entire silhouette of the Earth, the whole background. And there's just this thin layer of atmosphere that's absorbing sunlight and letting some sunlight through. What that atmosphere does is it interacts with light at very specific wavelengths. Each atom and molecule in the atmosphere of the Earth has a unique spectral fingerprint, which imprints on the spectrum of the light that has left the star, gone through the planet, and on its way to the James Webb Space Telescope before being split up by our prism and detected by our camera, is going to generate lines like these, which we can use to identify which atoms and molecules are present in the atmosphere of those planets. Finding oxygen by itself isn't enough. We're going to need lots of lines of evidence to say whether or not a planet is truly alive, right? We don't want the New York Times to run with our story that says, this planet has oxygen and therefore there are little green men. We want to do better than that. And so we're going to look for lots of lines of evidence that there's life on a planet. Like, if you were to look at the Earth's atmosphere is made of mostly nitrogen, some oxygen, and then a smattering of other things. It turns out that the combination of things that you find can actually be a good signal that there's life on a planet. Namely, here, oxygen and methane don't get along. If you release methane into the Earth's atmosphere, after a short period of time, the oxygen breaks it down. And so if you see both methane and oxygen in an atmosphere at the same time, that could be a sign that there's something producing methane in that atmosphere. The thing producing methane in this atmosphere is mostly cows. You guys are so good. What's producing most of the oxygen? No. Algae. Algae. It's actually coming from the oceans. Thank you to the 10 of you who knew the answer to that. But if you're looking at other planets in the solar system, if you look at our nearest neighbors, you'll find that Venus's atmosphere is made of carbon dioxide. And you'll find that Mars's atmosphere is made of... Ooh, I heard everything that time. It's also carbon dioxide. So when you look at the three planets and you look at the one in the middle, it's very easy to see that something interesting is going on there. And that's going to be your sign. That's what we're going to look for. We're not just going to look for the planet that sits in the Goldilocks zone, that's not too hot, that's not too cold. We're not going to just look for planets that have oxygen, because that's not enough. We're going to look for planets that are in the right place, at the right time, with all of the right signs. And then, maybe then, we'll start talking about life. But it's going to be really hard. The system that reminds us of how hard this is the TRAPPIST-1 system. This, when the 7 planets in TRAPPIST-1 were discovered, there was a press release that put out an image like this. And I love looking at this image because it reminds you that the system is actually really compact. The planets, as you would see them from any of the planets in the system, would appear large in the night sky. And the star would appear dim. And maybe, just maybe, one of the planets has snow and clouds and surfaces with continents and oceans, but we don't know that yet, right? It turns out we also don't know if the star looks like this. We're so used to imaging stars and saying, oh, well, they're mostly just uniform disks. But one of the things that my PhD thesis has been all about is that stars have spots on them. Isn't that exciting? Maybe not. But you only know as much about a planet as you know about its star. Because what you're studying when you study a planet most of the time is the effect of the planet on the star's light. And so if there's anything going on the surface of that star, it will influence your ability to understand its planet. Let me give you an idea of what that looks like on a star that we know really well. This is the sun. This is an image taken every 12 hours on the sun for 8 years from a spacecraft that's sole job is to stare at the sun. And what you can see is a lot of stuff is going on the surface of the sun. There are dark spots that rotate around the surface of the sun. The sun rotates with a period of about 26 days. And these spots are appearing mostly at 2 active latitudes. And these spots influence our ability to measure properties of planets. What is a star spot? I promise I'm not going to talk about magnetohydrodynamics for too long, but I am going to say that the surfaces of stars are super cool. On the surface of a star, what you see shimmering here on this part of the image is actually convection. You're seeing like boiling cells in a pot, except you're seeing plasma on the surface of the star doing the same motion. This is convective motion. And you can see these little blooms of convective plasma, which are rising up to the surface from their heat. They're radiatively cooling and then sinking back down in. And that process gets stopped by really strong magnetic fields. That's what's happening in the spot. You have a really strong magnetic field which prevents this convective motion from occurring and gives us these giant dark spots. The Earth could fit several times over within this dark spot. And that affects our ability to measure properties of planets. And to not belabor the point for too long, if you have a dark spot on a star, it's blocking out some of the starlight for you before the planet enters the picture. And so the amount of light that goes missing when the planet starts blocking out starlight is actually proportionately greater. That would be the same signal as if you had a slightly bigger planet. And so it's actually hard to distinguish between how large your planet is and what's going on the surface of your star unless you're super careful. And so I just spent the last 6 years studying those spots on stars and trying to figure out how we can learn anything about them from a distance so that we can make robust inferences about exoplanets. I have a lot to say about that, so if you have questions, I'd be happy to answer them. But in the meantime, I'm going to summarize, and I'm going to tell you that we're going to continue finding Earths by their shadows. The Earths are abundant. There are so many Earths out there. That's not the problem. We're going to find so many of them. We already have. The hard part's going to be characterizing them. And we're going to do that in a variety of ways. One of the ways that we're going to do that is with spectroscopy, with the new space telescope that I'm very excited about. And hopefully, when it launches in 2021, don't mark my words, when it launches in 2021, we will begin the process of collecting the data about the TRAPPIST-1 planets to figure out what kind of climates they have. And I'm super excited for that. But before I ask you to clap for me by saying thank you, I want to thank you. I want to thank all of you, because I've been coming to these Astronomy on Tap events for the last 50 events. And I've been at every single one minus like 3, I think. And you guys just keep showing up. And that's really amazing. There's this really wonderful thing that's happening in Seattle, which is like, Astronomy on Tap happens in a lot of cities. There are now more than 30 cities across the world that host Astronomy on Tap events. But it turns out that you guys are supporting one of the biggest Astronomy on Taps. We compete with 2 or 3 other events to be the biggest monthly regular attendance Astronomy on Taps in the world. And I don't know what that says about Seattle, but I love it. So thank you for coming out. Thank you for being here. Thank you for paying attention. I'd love to answer your questions. The question is, if you have planets orbiting a star in a configuration so that you can't see the transiting exoplanets, can you still discover those planets, or do we know how many of them are out there? Fortunately, a lot of people who are a lot better at math than me have figured out how to do the math to say, if we've discovered 2,000 exoplanets that are transiting, how many are there that aren't transiting? Given that stars are probably randomly oriented throughout space. And the number of stars that host planets that are likely rocky, that are slightly bigger than the Earth, between 1 and 1.7 times the size of the Earth, is 20% of stars. 20% of stars have a warm super-Earth orbiting them, which is a lot of stars. There's a lot of stars out there, which means there's a ton of planets. So to answer your question, there are so many planets. So many planets. Yeah. So the question is, what about moons? The moon seems relatively important for life on the Earth. We know that a lot of people believe that complex life might have evolved in tidal pools, and so maybe tides are important to life. It turns out that it's hard enough to discover a planet. A moon is significantly smaller than a planet most of the time, and so to date, there's one tentative detection of a moon orbiting a planet outside of the solar system. We're going to continue looking, but to date, we haven't been able to find very many of them. And that could mean that they are small or they're not common. But what we know in the solar system is that most planets have moons. So we expect most planets out there to have moons too. We just haven't found them. Where is that potential moon? That potential moon is orbiting a star with a name I don't remember. It's Kepler 1680 something. And it is a Jupiter-sized planet that appears to have a Neptune-sized moon orbiting it, which would be a really wacky combo if that's real. There's a big debate in the literature about whether or not it is real. Some of my friends think it is real, And I have other friends who have published papers who say it's not real, and those friends rarely talk to each other, and I try to stay in the middle. I don't really know if it's real or not, but we're going to keep looking and see if it shows up in more data. The question is, when we look for life, are we looking for life that's Earth-like life, or are we looking for any life? The answer to that question is that as scientists, our job is to find things that we can prove. And what we know is how life works on the Earth. So if we want to look for life elsewhere, we're going to look for life that mirrors life on the Earth so that we know what we're talking about. It's entirely plausible that life arises on other planets that has other genetic chemistry and is not carbon-based. All of that could be possible. But if that's true, we don't know what we're looking for. And so in order to have testable hypotheses about what we're searching for and whether or not we found it, we're going to look for life that looks like life on the Earth first. Then we'll worry about the other stuff later. The question is, can you give us an update on the rare Earth hypothesis? This is a book that was published by two professors at UW who believe that Earth is probably rare in that complex life may not be common throughout the universe, and that the most common type of life throughout the universe is probably not complex life like bacteria. There's not much I can add to the rare Earth hypothesis, apart from saying that it is a hypothesis that we intend to test. And we can test it by looking for global scale life on other worlds, the same way that we would look for complex life on an Earth-like world, which is we would look for the blue skies of an exoplanet, which represent the oxygen content of its atmosphere, which is produced mainly by algae, actually. So if you were to look at the Earth, you would find better evidence for not complex life than for complex life, unless you were looking at radio waves or some place where humans are actually making a lot of noise. The question is there a relationship between sunspots and the activity cycle of the sun? Is that the life cycle of the sun? Okay, and the life cycle of the sun. The answer is yes. When stars are young, they tend to have more spots, and those spots seem to be larger. And that might influence the way that we see planets. And this is something that I'm actually working on right now. If you have a lot of spots on a star, because that star is young, then it would appear that planets orbiting those stars are slightly larger because the star spots are also blocking out some starlight. And it turns out that the youngest stars that we've discovered that have planets seem to have large planets. And so I got really curious a few months ago whether or not we can explain the large size of those planets by the spottedness of their stars. It seems the answer is no. It looks like planets might actually start off puffy, which is in line with our expectations of how planets should evolve. Because when a planet forms, it's very hot. And the hotter a planet is, the more expansive its gas becomes. So its atmosphere is puffier and hotter. And that seems to be borne out by the data so far. And then as stars age, they get less spotted and they spin slower and slower. Do I think the Great Filter is real? This is a reference to the idea that there may be something which stops civilizations from becoming advanced. I think there is not enough data to say whether or not that is real or not. And as a scientist, it's my job to speak for the data and we just haven't discovered other planets inhabited by complex or not complex life to say whether or not that's real. So I'm going to punt on that and say we don't have the data yet. How can you tell a planet from a sunspot? There are a few ways. One way is that in my movie of the sun spinning around earlier, you saw that spots appear and disappear on the surface of the sun. Fortunately, spots only live a few weeks. And so when a spot appears, it might influence your data, make you think you're seeing a planet, but it will not be there by the second time an Earth-sized planet goes around. And because an Earth-sized planet orbiting a sun-like star takes 365 days to go around. So the chance that you're ever going to have a spot that mimics a planet exactly is actually very small. So they don't pose as big a problem as you might imagine in the process of trying to discover planets. Right, as long as you look for long enough. Question is, can you detect magnetic fields emanating from a planet or emanating from other stars? The answer to this question is yes, but it's very hard. Studying magnetic fields of stars has been done for a long time, actually, because stars are bright, and we have a lot of light from those stars, which we can use to try to study their magnetic fields. We find that many, especially young stars, have very strong magnetic fields, which we can detect from the Earth. It turns out that measuring the magnetic fields of planets is significantly harder because they're significantly weaker than their host stars, and planets don't shine very bright. So we're left with very little light to try to study them by. So far, we've tried to study magnetospheres of exoplanets by looking for one of two things. Either you're looking for plasma, which has interacted with the magnetosphere of a planet in the radio waves, or you're looking for aurora, which are emitting light from the surface of the planet as particles trapped on magnetic field lines careen into the planet's atmosphere. We found no significant evidence yet for either. We barely have tentative radio detections of exoplanet magnetospheres, and we don't have detections of aurora on exoplanets yet. But we're looking for them, and we might find them.
Will the James Webb telescope give us any information?
Will James Webb change that? I think the short answer is maybe. It might. I think there's room for some hope that James Webb could detect aurora that we have been unable to detect using ground-based telescopes. But I think that's challenging because those auroral lines would need to be in the near infrared, which is not where we're used to looking for aurora. So it would be a different kind of phenomenon than we're used to looking for. I'm going to call it a night. If you have any more questions, feel free to come up and ask me. Thank you so much for sticking with me.